So if any system is given a harmonic response, a harmonic input, and it changes the phase angle as well as the amplitude, and we can find it out. I want to show you the formula which is useful to find out the output response of a transfer function. So let me share with you the equations which we'll be using. For example, this is a mass spring damper system, and this is the transfer function for that. So the transfer function is the output or input, and in the Laplace domain. So please note it down. Now, if I show you, when we replace S by J omega, so if you plug in J omega or I omega is the same thing. So what I'm doing here, replacing S by iota omega, which is the frequency domain. And you know, we already have done this like work over here, like sinusoidal function can also be represented. The solution can be represented like a e to the st, where s is equal to iota omega. So now you plug this in over here into this transfer function over here, and now you get a frequency domain transfer function in terms of omega. The benefit of changing this from s to omega, that you want to see the response at a range of frequencies. Like if I give omega like sine omega t, so omega goes from 0 to maybe, for a very large number, what happens to the response. So we want to see, and the phase angle, what happens to the phase. So we can see that phase angle, and the formula for the phase angle is given over here. So let us find out some more formulation. So magnitude ratio, let me explain to what is m. Suppose if you have a mass, and if you want to see what is the output or input, the magnitude ratio, that is a, for example, this is a mass and you give input frequency um, f, and this is the output. So the magnitude ratio m is defined by the output or input, for example a static value, like if you take the forcing function as sine omega t, where the x is the range, x goes from, it depends upon the range, like uh, so over here the magnitude ratio, what is that equals to. So from here, if I take this transfer function equals to x over f. So this is also equal to the magnitude ratio. So now there are certain formulation I want to show it to you so that you should not get confused when you see such a homework problem. So just to see different uh, types of rearrangement and the conversion. For example, we know that zeta equals to, this is zeta, then the damping ratio, C actual damping divided by the critical damping. And critical damping is also known as 2m omega n, or 2m square root k over m, or if you write down like this m can be split up into two square roots. So this m is cancelled by this one. So you're left with 2 mk. So this is what it is. So we can write down like this, 2m omega n, or like this, c over. And let's see how we come up with a different other formulation. You already know the formula for the natural frequency is given by square root k over m. But how do you get this formula? So let me show you. The left hand side is 2 zeta over omega n. So how is it equal to c over k? So you know that I can write down like this. 2, this is zeta, correct? 2c. So I wrote down this formula, replace zeta by this formula. And now I'm writing down omega n. What is omega n? Square root k over m, square root m, correct? So this m is cancelled by this 2 is cancelled by this. So c over, did I make a mistake here? Look, c2, oh yeah, this is correct. C over, I have to do this one more time. I
You
think I
forgot
should.
divide by omega n.
Let me redo this over here. So let's see. 2 zeta is c over 2mk. Agreed. Now divide by omega n, which is square root k over m. So now it is so this m is cancelled by this m. You are left with c over k. Okay, so that's correct. Now I think there was a mistake before. So now you can see 2 zeta over omega n equals to c over k. Why are we doing this? To find out this ratio. Ratio is applied frequency divided by the natural frequency. So if you have a mass, so you are giving some input frequencies to this mass. Like I usually teach like in the lab, or I can give you the demo. If you have a rubber elastic rubber band, and you are holding this, the mass, maybe a bolt, and you have another rubber band here. So when you give displacement here, so this also starts moving. So if at low frequency, you will see the displacement at low frequency, and the output displacement and the input displacement, they are in phase. Like in phase means that uh, p is less than 90 degree, they are in phase. And we will talk more about it. But as soon as the frequency increases, after a certain value, the mass, the input is given like positive to the mass, rather than going downward positive, it goes upward negative 2. This happens when the frequency is higher enough and the phase is out by 90 degree. We will talk more about it in the Bode plot. So let me show you the next formula here. This is the next formula. R equals to omega over omega n, and the same equation which we just wrote down here, this one, this one can be now, you just take k outside the parentheses, so I can write down here. So let me write down here. And you see, this can be further simplified by omega square over, this is not square, this is k over m. What is this? This is equal to omega n square. So I can rewrite this into omega and omega n form. So I'm going to copy and paste that one into our book here, notebook. So let me show you. So this is the magnitude, the response, the steady state response when you are replacing mk by r and zeta. So this is the find how to find out the steady state response of an input function, and this depends upon omega. At certain frequency it is different than an other instant of the, like if you start changing the sweep signal like a chirp signal, the frequency starts from 0 to, maybe from 0 to 100 radians per second. So what happens to this displacement response, output response? So it is frequency dependent. And mm, just to tell you that at high frequency, this mass starts reducing the distance. Suppose I'm giving input like 2 centimeter from the top, but it will not move at high frequency. It will move like maybe zero point 0.3 centimeters. So the, as you go increasing, like if you see my hand, so I am giving input here like this, and then the mass will starts reducing its displacement at a high frequency. But as you keep moving slowly, the rubber band, imagine the rubber band is holding, or a spring is holding the mass. Imagine the spring is moving slowly, like 1 hertz, like 1 cycle per second. So the mass will move also 1 cycle per second. But as you start moving the input from your hand at a high frequency, the mass will not follow that after a certain time, so it becomes smaller and smaller. So the magnitude of the response decreases at high frequency and increases at a low frequency. And this is the phase angle, and this is the formula for that. So let me show you. So what happens to the phase angle? So over here, if this is positive, this is in the third quadrant. This is negative, it is in the fourth quadrant. The reason being is I mentioned earlier, the numerator has the phase here like a 0 degree. The total overall transfer function, the phase is 0 minus the value. So you can see that one. So this is the steady state response. It can be written like this form. So this formula you can use for your uh, homework problems. Now I want to show you what is the steady state, the magnitude ratio, steady state magnitude ratio for this mass spring damper system. So magnitude ratio is x over f naught, steady state. SS stands for steady state. So if you bring this down, like if you bring this down, so you're left with 1 over here, correct? 1 over k, and then 1 minus r square whole square plus 2 zeta r whole square. This is the amplitude of the. So for low frequency, like if you plug in input frequency like very low, almost uh, like r is at low frequency, the forcing frequency, r goes to r equals to omega over omega, and so this goes to 0. If it goes to 0, this goes to 0, so you're left with almost 1 over k. So m approximately equals to 1 over k. You know that if you have a spring and a mass, and what do you know about this displacement? The displacement is x, so F equals to k times x, or output over output is 1 over k. So it is similar to this one. At low frequency, it will behave like a static spring. And that's why if I replace, we usually call this as a static displacement when the spring is attached at low frequency. I can write down like a steady state displacement. So steady state displacement. So if I write this like, or if I write down steady state displacement, static deflection, sorry, static deflection is F naught over K. This is just a rearrangement. I want to show you um, the book, cut and paste here, that how did they derive this number formulation. So this is a static deflection in the spring, and M, you already know this is the output over input. So you can see that this one can be represented by Km, which is equal to 1 over K. So this K goes over here. So Km equals to, this is F over so this is just a rearrangement. I think you can easily understand this one is equal to this, and then this is equal to this. This K is so for R equals to 1, when you plug in 1 over here, what happens? This, you are left with this answer. So this X, okay, this is the response, and at any instant, this is not equal to static deflection. This is the response of the forcing function. So this response you are actually doing this dimensionless quantity with the 2 over 1 over 2 zeta. When this is a special case when r equals to 1. I want to show you the plot, how it looks like when you find out the magnitude ratio, and you can see at r equals to 1, you see, I believe this a large peak here. R equals to 1 means the forcing frequency is equal to the resonance. At that resonance, this mass will be at the highest amplitude. And zeta, if you keep on increasing the damping coefficient, it will start reducing the output response. This is my x over delta s, which is the output response dimensionless, is 1 over 2 zeta. I want to show you the second plot, which is the phase plot. The phase plot can be plotted by using this phase angle formula in the MATLAB. Yes, so this is the phase angle. So you see at r equals to 1, the phase angle from 0 to 90 degree, you suddenly, as soon as it changes from 0 to 90 degree, it means the resonance is occurring at that phase when there is a sudden um, deflection from positive to negative, you see. So you can easily look at the phase diagram, where is the resonance occurring. And for zeta, you see a sharp change, but as you increase the zeta value, the deflection will go slowly, as you can see in the magnitude plot, that the magnitude is smaller as compared to the larger magnitude when zeta is a smaller value. Have you understood the main idea, right? From the phase angle, you can see where is the resonance happening. So some other formulation, I want to just throw it here, that is going to help you. So one more formula, that the when you have resonance with the damper involved in it, so what happens when you have, if there is no damper, then resonance will occur exactly uh, r equals to 1. And when there is a damper involved, it is not exactly equal to 1, but it is 1 minus 2 zeta square. And if you plug in r, what is r equals? R equals to omega over omega n, and this is the value where you see the maximum maximum amplitude. The amplitude ratio is maximum when you have r equals to square root 1 minus 2 zeta square. And what is that? So the peak frequency, that is equal, this is a little bit smaller than the natural frequency, as you can see, 1 minus something. If you have zeta like 0 0.2, 0.5, it is omega peak is not the exact natural frequency when you are using the damper. In the damper case, omega peak is little bit smaller. So you see it's little bit shifting here. You see it's little bit, the peaks are coming little bit behind the actual value of r. You see, because of the damping coefficient. Resonance. it is still considered as resonance or high peak resonance. There is a good that there's a good point. Actual resonance happens when zeta equals to zero. But when you have zeta damping coefficient involved, then this is the frequency omega p, which is less than omega n natural frequency. That is a little bit smaller. So, and this happens when zeta is less than 1 over square root 2. So let me check. If you have 1 over square root 2, this is about 0.707. So this is the peak frequency. So so you may see some question where there is the question asked like, what is the peak frequency? You will use this formula in those questions. So I want to show you the table which you'll be using for solving some problems, homework problems. I will be able to solve some problems today. And you see the formula which we just learned uh, earlier, this omega peak equals to omega n, and related with that omega peak, like omega peak, what is the displacement over here? What is this displacement? We call this as um, peak response, xp. So this is the formula for that. If you plug in zeta equal to 0, if you suppose, for example, zeta, if just say, so omega peak would be equal to omega natural frequency. And in that case, the output response, the dimensionless, will go to infinity. And in this case, you see, this is a little bit less than 0, but a little bit greater than 0, but it's still almost. So this goes to our output response goes to infinity when zeta becomes equal to 0. There is no damping. That's why we use damper um, to reduce the damages in the machine at a certain frequency. Okay, let's do one question really quickly here. Let us solve question number 1. Please note it down. Question is the transfer function. Use the transfer function to find the steady state response given at the function. So if I go back to the formula,
You just passed it.
This one. Okay, let's use this formula. Um, I want to replace this s by iota omega, the transfer function. So let us see. And the steady state displacement is the amplitude times sine omega t minus phi. So let me double check this is the same formula which I'm using here. Can you tell me the mod of this, which is the output over input? So in that case, y over what is our forcing function? The forcing frequency is 0.01 radians per second. So I want to just replace it by iota square is just like minus omega square minus 0.01. I will say zero point zero 0.01 omega. This is omega. Now this is I have still not taken the mod. So if I take the mod, you can take a look here. So 5 over 1 minus. So if you do the math here, so this is 1.0. I would say let's write down 1.004 whole squared. This is the magnitude. So let's do this together. 5 divided by square root of 1, so 1.4 square plus. Can you verify? Do you get the same answer?
Yes.
And now this is equal to x over f. So the displacement, so I should have written here x over f times. So I will say this is my x over f And now what is x equals to? Let me write down. X equals to x over f equal 5 times 4.9, correct? That is my x. And now if you multiply this, sorry, this is not 5. This is the amplitude here. Is 20. 20 times, because the magnitude is equal to x over f, so x equals to t times f. This is my f naught, which is coming from this applied. I would write down like this: f naught sine omega t. So you have to multiply this by 20 to find out the output response. So let me write down x steady state equals to. Now what is phi? So we know that phi equals to minus tangent inverse. So what is the, this is my real part, this is my imaginary part. So imaginary part will come in the numerator for finding the phase angle. So imaginary part over the real part. 0.14 is almost 1. Let's do the math. Can you guys help your professor? So what phase angle do you get here? So arc tangent 0.14 with a negative sign here. So negative outside. I get minus 0.14. This is my phase angle, minus 0.14 radians. This is the, now let's pick up this formula. I want to use this formula to find out the final steady state displacement. So x was equal to 20 multiplied by 4.9, or 98. Omega in our case was the harmonic signal of 0.01 frequency, 0.01 radians. This is our steady state displacement. Do you understand that? I think you can solve the next question by yourself at home. I will leave this. Uh, I'm going to show you uh, what I'm doing here. So these are the two. I just solved the first part, but you should be able to solve this part B at home, which I think the homework problem. So let's do the next question. This is the mass spring damper system, and the equation has a, this is the mass equals to 5, damping coefficient equals to unknown, so it is not having any value. K equals to 10, and the forcing function equals to F sine omega t. So the magnitude ratio, sorry, this is M equals to output response divided by the input uh, amplitude of the force. Determine the natural frequency. You have to find out the natural frequency and the peak frequency and the peak frequency magnitude for two cases. For A, when zeta is point 0.1, B when damping coefficient a little bit higher than zero point 0.1. So now you know the formula. If I go to the table, please note it down. So if I go to the table, let's see another table. So what is my omega n? That is equal to square root k over m. Omega n square root k over m. K value is 10, m equals 5. That is equal to square root 2. And now let's plug in zeta equals to 0.1 to find omega p. And you already know, we know that this omega p has the peak frequency at which the maximum amplitude is occurring. It is given, it is little bit smaller than the resonance frequency. This is 0.1. That is equal to 1.4. And the peak amplitude is this response at that frequency divided by the force F. So can you find out XP, which is equal to XP over delta ST. This is zeta. Let me rewrite here. This is zeta. Is it correct? Can you verify this is, or am I doing some mistake here? 0.2. 0.2, 0.1.
Uh, d- don't don't
Oh
just
yeah.
divide by k?
Yes, you're right. We should divide by K. So the MP, so F and the static displacement is K as delta XP over K static deflection. So so if you do the math here, so I believe you should have taken like this. One minus zeta square. So divided by k, it is 0.5. Please note it down. This is the maximum amplitude which occurs. So maximum amplitude formula is this one. Let's go to the next small topic. We are left with a few more minutes. Sorry, today we started the class, but I'll make some small videos for the next section. The next section is about the dB value, how to find out the dB value of output response. So the basics is this one. So suppose this is m equals to 10 log to the base 10 m square. So this 2 will come multiplied by 10, and you are left with this 20 log m dB. And what is m? So this is a magnitude ratio. M equals to, this is the output force, this is the input force. Output force may be different than the input force, so I can write down this in the formula. Let me show you the formula here. Now, if I want to ask you, okay, guys, can you find out the magnitude ratio? So the next thing you can see, as you saw here, we understood that the magnitude ratio can be written in terms of dB. That if you take the log of this um, formula and multiply by 20 to get this answer will be in dBs. And how would you draw the plot in dBs? I want to show you the magnitude plot. I have made a small video how to draw the Bode plot in YouTube. I can share with you. Do you want me to share with you the link? How to find out the dB value of the magnitude or the corner frequency? Okay. You see, this was the plot over here. The output response without the dB. Okay. The same response you can plot with the dB over here. When you take log of 1, that is equal to 0, correct? You see? So this um, bump shows me that the resonance is occurring over here when omega over omega n equals to 1, and this is happening over here, and this shifts to the left as the zeta value keeps on increasing. This is the same plot, but now we are doing it in the dB value. You see the slope is decaying by minus 40 dB per decade because the function, if you have 1 over s square, the Bode plot will be negative 40 per decade, like from 0 or from 1 to 10. We call this as frequency of 1 decade, or zero point 0.1 to 1 decade here. This is the corner frequency. When the it hits the corner frequency, it starts changing its dB value, magnitude response. So I want to show you the phase plot. It will look like almost the same what we learned earlier. This is the phase plot here. Is almost the same what we just saw here. So we have finished this topic today. I'm going to make a small video about the bandwidth and the beating for you. Okay, thank you guys.
Professor, I had a question about bandwidth. Number 9.
Yes.
Zetas. Uh, how do you find bandwidth when zeta is about 3?
Number 9.
Yes. Um, technically, you can't find bandwidth because there's no peak if zeta is greater than 1 over square root of 2.
Mm.
But none of the equations work. And I watched your other videos that you posted on the assignment.
Okay. Okay, give me some time. I will do this at home and give you the solution.
Thank you.
Thank you. Bye bye.
Bye bye.